Now the problem is that, like she said, what if I now have 5 feet? Then I need another symbol. And what if I have 5 of those? Then I need another. And where does it end? Because as time progresses, quantities that I want to keep track of get larger. There's no end. I need a system that is sort of future-proof. But as the quantities get bigger, I don't want to remember more and more symbols. The Romans overcame that by the line over the letters method. So that stopped the symbols, the new symbols. The Babylonians, well, who knows what they did. Their system sort of had the efficiency built in that they had 2 symbols and then a place value to take care of bigger and bigger numbers. So if the number gets bigger, I'll just add more places and recycle my symbols. Counting the places would indicate what I do with it. So surely this is efficient. This is more efficient. Having a place value system. So let's say here, a place value system seems most efficient. And the Romans did that sort of in the background. It was a little more difficult to see the places, but it was there in the background. Whereas in the Babylonian system, it was more apparent. So I will have some places as well now. From right to left, I'll count the number of rocks, the number of fingers, the number of, what's next? Hands. I guess I shouldn't write the words, but the symbol instead. And then the number of feet, and I could keep going if I wanted to. So, in any single place, what are the options? In our language, I can have 0 of them. Like in these, I had 0 fingers. But if I have a place value system, now I'm going to have to keep track of that, just like the Babylonians needed to understand which place means what. I need an empty place symbol, and 0 is what we call. Of course, 1 rock is possible, but in any place they're the same, right? 2, what do we call 2, 3? How high do I go? In any single place, what is the maximum number of any single symbol? 4. Only 4. So my options are fairly limited, which is a good thing. Meaning if I want to convert this to a place value system, I only need to introduce symbols for 0, 1, 2, 3, 4. Whatever language you use to name them, my symbols are independent of the language. In our language, you can call them whatever you want. So, I'm just going to erase this. We need symbols to represent those quantities only. Much more efficient. That I only need that collection of symbols. And I can make any size number. Much more efficient. So to sort of be true to history and see and have a nice progression that links with that, we're going to create we're going to use the following symbols. Well, 0 as a number came to the forefront, really, or the awareness of people became more aware of 0 as a possible number in India, where the concept of nothingness was just as important as having something. And no one really knows, but it's believed that they would have a little placeholder stone to indicate an empty place, and when you take it away, it would make a little circle indentation, and that became the symbol that we call 0. For 1, I'm going to use a symbol like this. For 2, I'm going to use a symbol like that. For 3, I'm going to use a symbol like this. And for 4, I'm going to use a symbol like that. These are, in fact, what were used around 1000 AD called, or from the Devanagari alphabet. And over time, they changed, but these were actually symbols that were used. So, for example, next page, 7.2, number 1a, and we'll call these now as a place value system using these symbols, Devanagari symbols. They're just symbols. That's all it is. We have to just have a symbol to count how many of these things there are. And we recycle them by having different places, a place for each type of one-hand symbol. So, using the Devanagari symbols, given a one-hand system number like 1 hand and 2 fingers, what would it look like in this system? Can I squeeze it in here? You know, I think I can. How many places do we need? Well, from right to left, just do it like that. We need a place for the rocks. We need a place for the fingers. We need a place for the hands. And we don't have bigger symbols, so we don't need more places. So underneath here, I'm just keeping track of what place meant what. We won't write that for very long. So I have 0 rocks. I have, in our language, 2 fingers. And I have 1 hand. So that would be the representation of that number using a place value system. Place value system. And that would be exactly how, well, not exactly, very close to how they would write it. So, example time. B. So perhaps these symbols take a little bit of practice, and that's okay. B, I have a foot. How many hands? 2 hands and 2 rocks. How many places will my number have? 4 places. So put lines under them for now, emphasizing the places. Now you can go right to left to right, it doesn't really matter. I prefer right to left for safety for now, in the beginning, but it doesn't matter at all. As long as you know what each place is counting. How you fill them in is irrelevant. Rocks, we call them 2. You can call them whatever you want. That is the symbol. That corresponds to the quantity of rocks. How many fingers do I have? 0. Then how many hands do I have? 2 again. Then how many feet do I have in our language? 1. Curly. It's only because we speak English. You can speak any other language, and that representation would be exactly the same. It's independent of the language. It is its own language. The language of numbers. Does it make sense? And we're doing it in this way to emphasize that those are just symbols. Just symbols. You could have made other symbols, and they did. They changed through history. It's completely irrelevant. 3 feet and a finger. Now I'm going to do it without the places in one line. But I do count feet, hands, fingers, rocks. So feet first, in our language, 3. What would it be in French? What would it be in Spanish? It's irrelevant. The symbol is the same. It doesn't matter. Then I know that next I do have to represent the number of hands so that the reader can keep track of the places, and this corresponds to feet. If I don't have the hands, my places won't be correct, just like the Babylonians had that issue. And the number of hands, there are no hands. My symbol for nothing is a little circle. Then there are fingers, and there's only one. Just make sure that your 1 and your 2 do not look the same. And then I have 0 rocks. Same size, 0. It's a representation of a quantity. But regardless of how big the quantity is, I'm only going to use these symbols. It's much more efficient. Even if I had a symbol for 5 feet, and 5 of those, and 5 of those, I'm still using only these symbols. The places just increase. So it's much more efficient that way. Let's go the other way and then just pause, see if there are any questions. Again, I just chose these because these symbols, and then you can stop at any other point in history and chose the symbols they used there. They're all sort of linked in the Hindu and Arabic civilizations. And in figure 7.1, you can sort of see the progression, how it went from the 1st century to what we have today. It's just symbols. And over time, people get a little more relaxed or changed how they write it. Just like you have different writing styles, but they're all representing the same thing. So by having these symbols, I see similarities, but I'm reminded that they are just symbols. Now I'm going to go from the Devanagari symbols to the one-hand representation. Now I see it's a 3-place system. 3-place number. So I don't know which way you want to start. We are used to reading left to right, so I might as well get used to that. But in order to know what this place represents, I do have to go rocks, fingers, hands. So now I know hands. So one hand. How many fingers? 4. And no rocks. There you go. It's very easy because I'm only working with 5s. So it never really gets out of hand at any single stage. Do I read that as 200? No. There is no 200 here. This is what I call 2 and a 0 and a 0. So again, 3 places, so I know that's hands and nothing else. And C, oh, it's a little bigger. Right? Now I have 4 places, so I know from right to left it's going to be rocks, fingers, hands, feet. So I have 4 feet, 4 hands, 3 fingers, and how many rocks? 1. It's really not hard at all. You just have to get used to the symbols. Just like any other system, you have to get used to the symbols first. So we are inching ourselves closer to our decimal system, because our decimal system symbols come from the Hindu and Arabic system, and their symbols have evolved over time to what we have today. But we're using these to emphasize the symbol aspect of these digits, because we forget, we're so used to our numbers. Number 3 says, state the decimal number for the following Devanagari place value numbers. No, I'll take the book because I will not remember. We have this guy. How do I convert that to decimal? Is it 140? No, it's not 140. What is it though? Well, maybe I should use the one-hand system to form the link. This counted rocks, fingers, and hands. One hand, but a hand was how many? 25. And 4 fingers, and 0, you can say ones there if you want to. So we're now jumping over the actual one-hand system to our decimal system. And then you calculate this, whatever the calculator says, 45. So it's 45. Does that make sense? Okay, then it's just a matter of practice. B. Is it the same numbers?
Yes.
It's the same. Man, I'm lazy. I was a little low, sorry, or a little high. Is it 200? No. It is, in our decimal system, 2 rocks, fingers, hands. 2 hands, and a hand is worth 25. And nothing in terms of fingers, nothing in terms of rocks. You can write it or not, doesn't matter to me. Calculate that, and obviously it is the representation for 50. Then in C, did I write C down correctly? We have this guy, what's the next one? 3, and then a 1 to represent, now it's rocks, fingers, hands, feet. Feet were 125, so 4 groups of 125, 4 groups of 25, 3 groups of 5, 1 group of 1. Check if that's on, yes. For a total of, whatever you tell me. Calculator or not, doesn't matter. 616. So see, the representation of these numbers are very different than our decimal numbers systems still. They do not look the same. There's a very clear and strong link between them, but the representations for the quantity, they're not the same. Any questions on number 3? No questions? It's all crystal clear? Oh, all right. One more example, we have time. And then just let it sit. It is, in a way, a crossover lecture, getting us to the next, how we're actually going to look at it. But it's nice to have some history as well, sometimes. 4a, now we're going from decimal to the Devanagari place value system. So 37 needs to be broken up into groups of 5. So that's one group of 25. And I have how much left? 12? Did I take the same numbers again?
Yes.
Yeah. Man, there's no end to my laziness. So we have to remember to change the last one again. Put that pen before I forget. 526. Anyway, I totally forgot, so I'm going to do them again. One group of 25, then two groups of 5, and 2. So my place value system will have 3 places. 1, 2, 2. We're going to squeeze one in here. Maybe we can. B will go over there. B was 128. Yes, you can look back in your notes, but let's do it again. One group of 125, then I have 3 left. But I'd like to emphasize that I have 0 25s. Oops, that's a 5. That's also a 5. 0 5s, and then 3 1s. So this representation will be the symbol for 1, 0, 0, 3. One more, we changed it to 520, what? I can't remember. 526, that's what I wanted to say. 526. 526 we have to break up as 4 groups of 125. What was left, we said? 26. So I can fit in one group of 25. Then I have 1 left, so no 5s, and 1, 1. And therefore the representation is symbol for 4, symbol for 1, 0, 1. So the only other thing to note here is that this is 5 to the power of 1. The next group, just like we had 60 and 60 squared, this is now 5 squared. And that guy is 5 cubed. And if I keep going, the next one would be 5 to the 4. So the places, the quantity that each place is counting is groups of powers of 5. And we can call this base 5 system, because we're counting in 5s. The base is the size of the group that we're counting in. So we have slowly converted from our one-hand system, for example, 2 hands, a finger, and 3 rocks, to a place value system where we're not making these symbols, we're rather counting how many there are in places right to left as the value of the symbols increase. So the number of rocks will be now represented by symbol like that. And of course, over time, those symbols changed. It started, if you look at the table, after exercise 7.2, it started with 3 lines. And then they made it a little curvy, and over time, depending on the area and the civilization, the symbols changed and evolved. But what they're representing stays the same. Then you're representing how many fingers there are, and we can use a symbol like that. And that evolved as well, from a horizontal line to something that looks like a 7 to a little curvy line. If we're using these, then you keep going and represent the next symbol up, which will be hands, which counts a quantity of 25 each. And there are 2 of them in our language, and you have a little symbol like that maybe, and that evolved too. 2 lines, a little less curvy, then got a little curl. And over time, these evolved to, you have your 0, that over time evolved pretty much not at all, stayed 0. The classic little circle indentation turned out to stand the test of time. The 1 quantity did change a little bit. Now we fancy write it like that, but also just a line if you want to. That's how we write it today. Or just a line. Out of laziness, really. Then the quantity 2 also stood the test of time very well. Not everyone writes it with a curly little bit, but I do. For no reason whatsoever. And then the quantity 3, which was represented by this symbol, really stayed very close. Just dropped that little tail, which was a little unnecessary. They're just symbols. The symbols evolved to what we have today. They're nothing more. The 4 changed quite a bit to what we have today, but they're still symbols. The problem is that we're so used to them that we don't see them for what they are. We see them as something else. They're just symbols representing quantities like these. So this would then be represented by a 2, a 1, and a 3. The problem is to distinguish this from our decimal system, and to prevent us from reading that as 213, we have to say, look, we're counting in 5s here. So we're going to write a little subscript to remind us that it's not 213. That is 213 base 5. And we're calling that, like I did last time, a base 5 representation or number. It's a representation of a quantity. That's what numbers try to do. And we can do that with Roman numerals. We can do that with Babylonian. The quantity stays the same. Its representation changes according to the number system. So please, for the love of everything good and pure, do not say 213, because that's not what it is. We're counting in 5s, and that has to be indicated so you don't misread the representation. Any questions on that? But it does force us to really look at what this number, how this number is representing a quantity. That what the places are representing tell us what the quantity is. And we're so used to our numbers, we forget that in our numbers we're counting in 10s. We forget. We're so used to it. We look for shortcuts to use our numbers and forget what they actually mean. So this is now using familiar symbols, but it's still a little outside of our comfort zone, so that we can really critically look at this place value system that we're using. And by counting in 5s instead of our familiar 10s, we're doing just that. So it may take a little getting used to, but there's very little difference now. We're only counting in fives. Our symbols are now the same. Everything is as close as possible, while still putting us a little outside of our comfort zone. So the questions are now the same. Convert back and forth, do the three types of arithmetic, and that's it. Same as for Roman, same as for Babylonian. So let's just go through it. Number 1 in exercise 7.3, we're converting from base 5 to our decimal numbers. So 1204 base 5, and if you don't have that subscript, then it's a different representation. You need that subscript. Now I'm counting the places. So from right to left, it'll be the 1s, the 5s, the 25s, the 125s. Now you can write them from right to left, but it doesn't really matter, as long as I group the digit with the correct quantity. 2 groups of 25, 0 groups of 5, and 4 ones. Just make sure I'm on camera here. So that would then be equal to, or this corresponds to a quantity, which is then equal to whatever Mr. Calculator says. What does the calculator say? 179. No subscript? So that is read as 179. And those two representations represent the same quantity. One, 3, 2, 1, 4, base 5. Corresponds to, now from right to left, 1s, 5s, 25, 125. What's next? Ones, 5s, 5 squared, 5 cubed, 5 to the 4. Let's write them. You don't actually need to know what they are if you want to use the calculator. 5, so one group of 5 to the 4, 3 groups of 5 cubed, 2 groups of 5 squared, 1 group of 5s, 4 ones. Calculator says it would be a little faster on the calculator if you know those powers of 5. What is 5 to the 4?
625.
625. And it's handy to remember. It saves a little bit of time. So you don't have to type in 5 to the power of 4. You just write 625. Well, I guess that's 3 button presses regardless. Easier this one though. What is the answer that I get? No, I get no answer. Calculator has a blank screen.
I got 1,059.
1059, she says. Can anyone confirm that?
Yeah.
Yeah. Good. It's worth doing here while we have the time, and then you know you can do it. You don't have to practice that more afterwards. Or if you do it and you get a different answer, you know, okay, I need to just go and practice that a little bit so it doesn't slow me down when the test comes. One more. C, 1003 base 5. That corresponds to, well, I'm counting 1s, 5s, 25, 125. So one group of 125 plus 0 groups of 25 plus 0 groups of 5 plus 3 ones. That's easy enough, 128. So again, I say for a test, I am really only looking for 128. But if you made a mistake by accident and you calculated 127 or something on the spot, then I can't give you part marks if you don't show how you got there. So I can identify, oh no, they did break it down correctly, it was just a silly mistake. So I'll subtract the minimum. But if you show no work, then it's all or nothing. It's all or nothing. Any questions so far? Sometimes the more familiar symbols make it a little more confusing. You have to really remember what kind of groupings are you counting. 2a, so now I'm going to convert the other way. Given a decimal number, what is the base 5 number? If I have 116. So, just like before, especially the Babylonian system, I suppose, we had to take that decimal quantity, break it up according to the group size, which is 5s in this case, and then convert. That tells us what the places, what digits go in the places. So what is the largest power of 5 that can fit into 116? Just 25. How many 25s can I fit? 4 25s. How do you know that? Worst case, use your calculator and say 116 divided by 25 and you'll get 4 point something. That tells you 4. How much is left over? Well, 116 minus 4 times 25 is 16. And again, do the steps so that in case you make a little mistake, you've shown that you do know how to do it. And you should get marks. So I have 16 left that I can break up further. That is 3 groups of 5 and 1 left over. So this number has a base 5 representation of 4, 3, 1, and you have to write the 5. Otherwise it's 431, which is not the same. Have a little bit of practice. It's really not anything that can't be mastered. And our numbers won't get that big. Any questions or comments on that? It's too easy. We took our time and we developed this carefully so that when we get to this point, it's as easy as possible. B. B is 789. What is the largest power of what is the largest power of 5 that can fit in there? 625. Only one of them. And it is, in my opinion, easier to think of 625 instead of 5 to the 4. But whatever works for you. How much is left? Well, 789 minus 625 is 164. Don't try and do everything in one step, though you can if you want to. Then I'll break 164 into the next piece, which uses a 125. Clearly only one group of 125 with how much left over? 39? All right. Just making sure I'm hearing you right. Now I just copy everything down, blah, 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 so that I can work with my 39. And the next grouping is 25, and I can fit one group of 25 in there. And I'll have, how much left? 14. I'm just checking if 14 is on the camera. Yes. I know I'm writing a lot of detail, and you don't have to write that much detail as long as you're doing everything correctly. Copy everything down, work with the 14, which will be 2 groups of 5 and 4 left over. Therefore, the base 5 representation of 789 is 1, 1, 1, 2, 4. Base 5. The amount of detail that you show is up to you. Depends on your comfort level. If you're not comfortable with it yet, show more detail, because the more you write down, the less you have to keep track of in your head. Give yourself the best chance possible. That was B. C is even bigger. Oh man. 3,186. So I need to check. I know now that 5 to the power of 4 is 625. What is 5 to the power of 5?
3,125.
And that can fit. I need to fit the highest power of 5 in, otherwise a digit will be greater than 4 and that's not allowed. So then I have how much left? Not that much.
61.
61. So then we're, whoops, not possible. Then we're copying this down. What's the biggest power of 5 that can fit into 61? 25. I can fit in 2 of them. And I'll have, that's 50, so I'll have 11 left. Let's not skip any steps so that your notes are complete and you can use it as a very clear, detailed reference. 11 will be 2 groups of 5 and 1 is left over. Therefore, I look at the digits, 1, 2, 2, 1, base, 5. Remember to always write the 5.
Yeah.
Man, you guys are too fast. I'm trying to trick you. No, can't get anything by you. You have to, if you read this, or if you say that's the representation, now we're counting 1s, which is correct, 2 5s, which is correct, 2 25s, which is correct, 1 125, which is not what we're trying to do. We have to, for safety, say here, there are no 125s. There are no 125s. So that I see that there has to be a placeholder for the 125 place. Otherwise, my representation is not correct.
And what about the 25?
Still, I just can't. I'm trying to trick you. It's not working. I fail. Sorry. Let's make more space here. There's also a 625. So to make it easier for yourself, you have to say, well, you don't have to. I would like to say that there are no groupings of 625 and 125, but there was a 3125. And then I'll just copy it here for the sake of being complete. And then I'm done, and I can say 1 0 0 2 2 1 base 5 is the correct representation. All right, clearly this is fairly easy for you, which is good. Good. 100% quiz, here we come. Get it while you can. Makes the final exam just so much nicer as an experience. If you go in with 40-something% already, pressure is way, way less. And you can just enjoy it. And you'll actually do better that way if you have less pressure. Didn't we do that already? Oh, that's number 2 is done. All right, nice. So, now the only thing left to do, we're staying in this base 5 number system. And we want to practice our arithmetic. Is that 7.3? 4? Wow. 7.4 number. No, there's only one. We're just doing addition. The method is the same. Roman, Babylonian, they're all the same. So I want to line everything up. 2, 4, 1, 0. Plus 2, 4, 3, 0. Always write your 5s. Otherwise, if you don't have a 5, I'm reading it as 2,430, which is not what we're doing, so I have to subtract something. Because I can't tell. Do you think this is decimal? I don't know. So you have to write your subscripts. Is that right? Yes. So, right to left, 0 plus 0, 1 plus 3 is 4, 4 plus 4. In our language, yes, we call that quantity 8. But in the base 5 number system, there is no 8. I'll do it on the side here. 4 plus 4 is what base 5? Well, it's the quantity we have a name for, but here they don't have a name for that. It'll be one group of 5 and 3 left over. So 4 plus 4 is 1, 3 base 5. It is not 13. I think you guys are struggling with that, just saying. Not 13. So there's a 3 that stays and a 1 that's carried over. It's getting much more familiar, much closer to our decimal system. We don't have little wedges and things, though I do miss them. Now I have 1 plus 2 plus 2, 1 plus 2 plus 2. We have a name for that. Base 5 system doesn't have a name for that as a single quantity. What is the base 5 representation of 1 plus 2 plus 2? 1, 0. Which means the 0 goes there, 1's carried over, but nothing else is there, so it goes straight down. Any part of that that feels less than perfect? So using base 5, we really have to look at this carrying carefully and really understand how this addition works, which makes us so much better at explaining it one day. Because for little Timmy, base 10 is just as far as anything else. It's brand new. To you, it's super easy. You know, why aren't you getting this, Timmy? Carry over the 1. What's wrong with you? It's brand new. So you sort of get an appreciation, perhaps, what it could feel like. Because I don't remember what it feels like doing this for the first time. It's too long ago. We've done it too much. We forget. And we have to remember that when we are teaching it, that it's not easy. It's not easy. B110 plus 4, 2, 3, 4. My 5s get a little shaky because I'm writing so fast. Anyway, method's the same, right to left. 0 plus 4 is 4. 1 plus 3 is 4. 1 plus 2 is 3. 4 is on its own. That may have insulted you because they're so easy. I'm sorry. I didn't know there was no carrying. Why do I have that as an example? Not every example has carrying. Some people, they go in thinking, oh, I'm going to have to carry stuff and do fancy things, and sometimes it just doesn't happen. That was a very easy one. And the quiz questions are generated randomly, so you could get one. Don't know. Some have carrying, some don't. C, 1, 4, 2, 3, plus 1, 0, 0, 4. Right to left, 3 plus 4 is what base 5? I have a name for it, it's 7. But here, there's no name for it. It's one group of 5 and 2 left over. Which means the 2 stays in the 1s column and the 1 is carried over. 1 plus 2 plus 0 is 3. Nothing carries over. 4 plus 0, 1 plus 1. Now you write that down, you think it's perfect, you get the quiz back, you lost 1 more. You have to write your subscripts. Otherwise, the number is read as a decimal number, which is not the case. So don't come back and argue if you wrote missed subscripts, but only 1 mark will be deducted, not 1 per. Yes?
If we go into decimal system like 3 plus 4 equals 7, and then write it down as like...
Okay, so sorry, I should have said at the beginning, the same rules apply as it did in the Roman arithmetic, Babylonian arithmetic. If you write digits other than 0 to 4, then that's an automatic minus 1 per digit. Which, because it means that you've converted, you did something in decimal, and the goal is to stay in base 5. So yes, I say in my head 7, but I can't write 7.
Yeah.
But luckily we're only working with 5, so it's not ever getting that big, like it did in Babylonia, that got a little out of hand maybe. So yes, you're not allowed to write anything other than base 5 numbers, which means anything other than digits 0 to 4. There are no other symbols in this number system. In our decimal system, we're counting base 10, so we have 10 symbols. In this one, we don't. Anything else?
Yes. On the quiz, will we be converting from the symbols or will it already be in the...
So, the quiz will not have one-hand system symbols. It will not have the Devanagari symbols, those which will cross over to get to this. So it'll be Roman, Babylonian, base 5, and then what we do tomorrow. Make it a little easier. What was this? 7.5. Same thing, we're practicing subtraction. Same method. We're just really making sure we understand how subtraction and borrowing works. So hopefully these have some borrowing. 3201 base 5 minus, where are we now? 2204 base 5. Oh, that's a big one to start with. That's okay. We can handle it. Method for subtraction is the same, right to left. 1 minus 4, that is definitely not going to be good. So I have to borrow 1, but I don't have 1. So I'm going to have to borrow 1 from the next, the left column, left to that, which means I have, I'm going to write that here as 1, 0. This changes to a 1. I'll just write a little f. Everything's in base 5. It's so small that a whole subscript is a little messy. What is that 1, 0 quantity now that I have in that second column? It's 5, but I can't write 5. If you want, you can make 5 little dots. 5 little rocks, if that, some people like that, instead of the 1, 0. You can choose. I'll say here, or write the representation, or because we're working with small quantities, you can just make some circles. Because this is linked to the one-hand system, so that's acceptable. They are the same. They are the same. You just can't go to decimal. That is the thing I'm trying to avoid. You can't convert them to decimal, do the subtraction, convert back. So either one of those, it's fine. I have the same quantity here. Then I'm borrowing another 1. So I have this 1 plus the group of 5, or you can say, or you can draw them with a diagram, that's okay, because this is essentially the one-hand system. There's no real difference between them, other than efficiency. It's not a fundamentally different system, whereas decimal is a fundamentally different system. So we borrowed a 1 there. Let's not write that. We always borrow just 1. Now, so this gets updated here. When I borrow a 1 from this, it changes. I lose one of the rocks, so this changes to what? 4. Let's write that, I don't know where. Squeeze it in somewhere. Does it make sense what I wrote there? It gets updated all the time, which was a major drawback in the clay in the Babylonian case, but it's okay. I had to borrow earlier on, which decreased this by 1, so now I have 1 in that column. I had what we call 5 things, because I didn't have anything. Once I borrowed 1 here makes 5 in the next. But then I borrow from that, so I only have 4 left, but this gets increased by 1. There was only 1. Another group of 5 makes what we call 6. I just can't write 6. So now I have these 6 things, take away 4, and I'll have 2 left. Then I have 4 things, take away 0, 4 rocks. Then I have 1, take away 2. That's not going to work either. Now I have to borrow from the 3. The 3 becomes a 2, and this gets 1 extra. Or 5 extra with the 1 I had makes what we call 6. There's just no 6 here, but you can do them as singles. 6 minus 2 is 4. 2 minus 2 is nothing. Maybe a little step up with the borrowing, and it's just keeping track of what did I use, what do I have left, what do I now have in total once it gets stuff, once it borrows something. It always just borrows 1, but once I move it over, it splits into 5. How does that feel? A little more confusing. Yeah. No idea? Well, it's our first example, right? And it wasn't an easy one. I should have started with an easy one. But I don't think it gets much worse than that. That's the good news. So we can look back at this one. Let's look back at that one once we have some easier ones under our belt. This may be just a one borrow case. Oh, B doesn't look any better. C, whatever, those aren't. C, well, let's just do it. How do you learn to swim? Get thrown into the deep end and see what happens. No, kidding. Although, I guess that is a strategy. Perhaps not the safest strategy. 3110. I'm going to move it lower. I was extremely high there for some reason. Not because I was smoking something. No? Tough brand, tough brand. 144, I forgot. Oh no. Here I am high. Minus. Now leave some space at the top. We've learned something now. We've learned, give yourself space at the top. That was an important lesson. Not really space at the bottom, because that's just the answer goes there. All right, did I write this down? All right. So, 0 minus 4, nope. I'm going to borrow something, I have nothing left, that gets a 1, 0, or just the 5 rocks that came from the previous column, because nothing else was there. So you choose which one, you don't have to do both. You choose which one you like. Make it as easy as possible. I'll let that go. So you have 5 things minus 4 is 1. Now I have nothing here to take 1 away, so I have to borrow from this. But there is 1 at least, and that now becomes 0. So that becomes 1, 0, or the 5 rocks that I borrowed from there, that's all I have. Take away 1, so I have 4 left. Now I have nothing here, and I'm trying to take away 4. So I have to borrow 1 from there, giving me the 5 rocks with nothing that I had. And this becomes 2. 5, take away 4 is 1. 2, take away 1 is 1. Just takes practice. Just takes practice. That was maybe a little fast. I apologize. I got excited.
When you're borrowing, like technically wouldn't that be like the ones column, 25, like 1, 5, 25?
I know. I get the question every time.
Why is it that you're only taking 5? Like wouldn't it be a good be 25?
It's a convenience of the method, really. Let's go decimal as an example because it's so familiar. 213 minus 78. Familiar, everyone can do it. You can do the method, it's comfortable, it's decimal. Here, 3 minus 8 doesn't work. You take what you borrow 1, so you have nothing left there, and this becomes 13. Yes, you sometimes write the 1 there, but I'll just write the 13. Now I can take 8 away to get 5. What? No, I'm done with that column. Now I'm working in this column with the 0 and the 7. How do we talk about this column? We say 0 minus 7. We don't say 70. We say 7. Because we're working in this column as if it's the ones column. Say, okay, that's not good enough. So I'm going to borrow 1 that makes this 10. We don't say it makes it 100. Just for convenience. 10 minus 7. Even though it is 100 minus 70, we don't need to say it. It is 3 instead of saying 30. And then 1 left over. Because once I'm in a column, I can see it as if it's the ones column and everything works the same. Because it's only coming from the left that I may need something. Once I'm done with this column, I never look at it again. I move on as if that's the ones column, and every one works the same. And that's why I can sort of recycle this as if every column is rocks, which in reality it's not. So it's a little convenience that comes out of the method. And the place value system. But in truth, yes, we are counting fingers and hands. But there's no need to do that. Though you can if you want to. There's no need for that. Just like there's no need for that here. Any other questions? Comments? Maybe one more example. Subtraction seems to be pushing against our comfort level. We have to find that limit and then push it a little bit. C. C, where is C? 3, don't be high when you do subtraction. Won't go well. Leave space at the top. 3040 minus 2333. Okay. What does our time look like? It's not bad. All right, 0 minus 3, no bueno. I don't have enough. So I borrow, now I have only 3 left. Do you prefer the base 5 notation or the rocks? Let's come in.
It's fine.
Base 5, she said. All right. This becomes now, I like to update it instead of putting a little 1 there. I've never liked that. It's a shortcut that's completely unnecessary. Now, remember that is not a 10. It's 1, 0, which is the quantity I have a name for. It's 5, minus 3 is 2. I'm not going to subtract anything if you don't have your little subscript in those little notes at the top. But not having it can very easily make me do a 10 minus 3. Then you're losing marks all over the place. 3 minus 3 is 0. 0 minus 3, oh, nope. I need to borrow. That then becomes a quantity of 5. Minus 3 is 2. 2 minus 2 is 0. I didn't need that much space. You need more space at the top if you're doing the rock approach, which you can totally do. Do not think for a second that that is a 10 that you're subtracting from. Thoughts? Maybe some practice required for that one. Let's go back to the perhaps easier multiplication because it doesn't have any borrowing in it. It's just fancy addition when you really think about it. Yes, the numbers get a little bigger, but we handled it in the Babylonian case, so clearly now it's just going to be easier. 7.6 A. Okay, 3041 times 2. If you have a single digit, you don't need a subscript because 2 is a 2 is a 2. It's always the same. What's our method? 2 times 1 is 2. Now I'm going to go 2 times the next place, so I pad that with a 0. 2 times 4. Let's do it on the side. 2 times 4 is what base 5? 1, 3. So that'll be a 1 and a 3. Now I need a subscript. Single digit, I don't need a subscript. You can have it if you want to, but you don't need it. Then I go 2 times this place, so my answer is going to start there, so padded with zeros. 2 times 0, 2 times 0. You can have that, it's fine. Doesn't matter. It's not my final answer. Then 2 times 3 is going to start over there, padded with zeros to keep everything lined up well. 2 times 3. And remember, I can write these notes because none of them is in decimal. 2 times 3 is 6, but 6 has a representation of 1, 1. So 1, 1. Now add them up. 2, 3, 1, 1, 1. So you need to be a little high to do this. You don't need anything in the top. But you do need space here because of my detailed addition. Again, this is the detailed version of the multiplication. There is a short one where you can just write the answer, make little notes, but unless you're super comfortable with it, I would not bother with that, and I would definitely not teach that. Though people do, it does not add to any understanding. Does that feel easier or more difficult than subtraction? I think easier, yeah. B. B. 4, 2, 0 times 3. 4, 2, 0 times 3. And again, that second number I'm going to keep as a simple number. Okay, 3 times 0, 0. I don't need a single digit. 3 times 2, so I'm going to pad it before starting. 3 times 2 is 1, 1. That is 5. 3 times 4, I'm going to pad that over here. 3 times 4 is? Ooh, I thought I heard a 22. Don't ever say that. 2, 2. Add. There's almost no carrying. Very rare to have carrying over in most multiplication questions. It's pretty straightforward. It's just the borrowing that presented some potential problems. But you might not get any subtraction in the quiz. Who knows? I don't know either. I'm randomly selecting them. Might be subtraction, might not be at all. It'll be a little surprise. C is 1401 times 4. So I go 4 times 1, 4 times 0. Before I even think about it, I don't need to pad it. But 4 times 0 is 0. 4 times 4 will start over there, so I'm going to pad that with zeros. 4 times 4, I'll emphasize 0 on the side, you don't have to. What is 4 times 4? Base 5. Four times 4, base 5.
3, 1.
3, 1. 3, 1. Then 4 times 1, we'll have padded zeros here. Whoops, that got out of hand. And 4 times 1 is 4. Well, this one has a little carrying over. 4, 0, 1. Whoops. 3 plus 4 is what we call 7, but there is no 7. It's only 1, 2.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.